Hey guys, today we're looking at polynomial functions starting unit 4. So a polynomial function is a mathematical expression of one or more terms, each of which consists of a constant multiplied by one or more variables raised to a non-negative integral power. So that's basically just a really fancy way of saying that it's a bunch of terms that are added up together. It could have a constant multiplied by a variable, so x or y or z or whatever letters, really. Usually it's x. And it's raised to a non-negative integral power. So when we say non-negative, that means anything positive or zero. And integral power means an integer, so no fractions, whole numbers here. So technically it could be x to the 0 power, which would just be a constant, so just some number. So keep that in mind as we're going through this. When we're talking about it being in standard form, that would be from the highest degree to the smallest degree. The leading term is the term that has the highest degree. And our constant, like I was talking about, is the term that actually doesn't have the variable. So that would technically be like x to the 0 power, but we don't actually write the x part. So that's just like the +8 or the +25 or the whatever number on the end, like the c part when we had our quadratics, ax squared plus bx plus c. So our constant is the term with no variable. So we're talking about polynomials. The graphs have special characteristics. So example 1, it says which of the graphs could be a graph of a polynomial. When we're talking about polynomial functions, because they have non-negative integral powers, there are certain characteristics. So one of them is that it has to be continuous. That means that we can not have a part and then a separate part. So we can't have any jumps. So this one would not be a polynomial function for A. And then another thing is that we don't have any sharp turns. We don't have any sharp edges. So C would also not be a polynomial. But if we're looking at B, it's nice and continuous. There's no jumps, no sharp edges, no sharp turns. So B is a polynomial. And same thing for D. It's nice and continuous, no sharp turns, no sharp edges. So D is also a polynomial function. So the graphs are nice and smooth and connected. The other thing about polynomial graphs is that when it asks to find the real zeros, your real zeros are going to happen wherever it touches the x-axis. Notice it says real zeros. Keep in mind we do have complex zeros or imaginary zeros, and we will get into that a little bit later in this unit. But real zeros are where it touches the x-axis. So if I'm looking right here, it happens at -3, 2, and 5. So the real zeros would be x equals -3, 2, and 5. Okay, the next part says multiply out f of x equals x plus 3, x minus 2, and x minus 5, and see what you notice. So if we're looking at the first part, x plus 3, that kind of corresponds with our -3, 0, because if we have x plus 3 and we set it equal to 0, that would get us -3. So that x plus 3 is going with -3 being an answer. If we're looking at our 2, that would go with our x minus 2. So x minus 2 would match with +2 being an answer. And following that same pattern, if I have 5 over here, that would match with our x minus 5. Oop, wrong color. That matches with that 5 as an answer. So if we were to take this and multiply this all out, I would start by taking these two right here and FOILing them out. So that would get me x squared minus 2x plus 3x minus 6. and I still have the x minus 5 behind it. Then I can combine my like terms and I get x squared plus x minus 6, and x minus 5 is still behind it. And then when I multiply this one out, notice that we have 3 terms in the first parentheses and 2 terms in the second parentheses. So we've got to take that x and distribute it to everything. So x times x squared is x cubed. Then x times x gives me an x squared. X times negative 6 is minus 6x. And I've got to take it and I'm going to multiply the negative 5 times everything in this parentheses. So negative 5x squared minus 5x and plus 30. From here, I can combine like terms. I only have 1x cubed term, so I don't have anything to combine that with. I do have an x squared here and a minus 5x squared, so that's going to give me a negative 4x squared. I've got a negative 6x and a negative 5x. That's going to give me a negative 11x. And then I've got a 30, and that's the only constant term I have, so that's going to be by itself there. And you'll notice that this that I get right here when I multiply all that out matches that equation up there. So your zeros are like the factors, just kind of how we talked about with our quadratics as well. And it's where it touches the x-axis. So we can use that to kind of help us with example 3 right here. It says consider f of x equals x plus 1 squared and x minus 2. Find the x and y intercepts of the graph. Use the x-intercepts to find the intervals on which the graph of f is above the x-axis and the intervals on which the graph of f is below the x-axis. We've talked about this a couple times. If we're talking about it being above the x-axis, remember that's where we have our f of x is greater than 0. And if we're talking about it being below the x-axis, that's where we have our f of x is less than 0. We talked about that back in Unit 1, and you had that on a couple of your My Math Lab homework questions in our past unit. So our x-intercepts kind of help us figure that out because our x-intercepts, remember, are where it actually equals 0. So if I find my x-intercepts, that's going to be where it's on the axis where it actually equals 0. So I can say that my x-intercepts are at -1, 0. Let's write that a little bit better. -1, 0, and at 2, 0. My y-intercept is where it touches the y-axis. So that's going to be at that 0, -2 point. And that's not really going to help me for the where is it above the axis and where is it below the axis. But it is still an important feature, so it's nice to know how to find that. But the x-intercepts are really what's helpful when you're trying to find where it's above the axis and where it's below the axis. So if I'm looking for where f of x is greater than 0, that's going to be this part of my graph over here, where it's above the axis. So if I'm looking for where f of x is greater than 0, I'm looking for my x values that make that happen. So I'm looking for the domain intervals. So it touches 0 at my point 2. So I would say everything greater than 2. So I'm going to use a parentheses because it's just greater than 0, not greater than or equal to 0. But I'm going to go off to infinity on the right. So we start at that point 2, 0, and then we go off to infinity. Where it's below the axis is everything on the left here, and then in between those two x-intercepts. So when I'm writing where f of x is less than 0, I have to use a union here. I would go from negative infinity until I hit that point at -1, and then union -1 until I hit my other x-intercept at 2. So we're finding the x values that give us certain y values that are either positive or negative, greater than 0 or less than 0. There are some other nice characteristics that come with polynomials. We're going to look at that on the next page. It says if R is a 0 of an even multiplicity, so that was weird. What that would mean is that we have like x minus a number, and specifically minus r. We're saying that it's r, but it's raised to an even power, so squared, or x minus r to the fourth, or x minus r to the sixth. It's an even multiplicity. Then the graph touches the x-axis and it turns around at r. So what that looks like, you can draw it over here in your box. It's going to turn around, which means let's say that r is right here. It's going to not go through the axis, but turn around and bounce off the axis. It could bounce above, or this time, let's say that r is over here. It could bounce below. Oops. It just kind of depends on what the polynomial is doing at any given time. And your r could be positive or negative, so it could be x minus r, or it could be x plus r. If r is a 0 of odd multiplicity, so now if I have x minus r to the first power, or x minus r to the third, x minus r to the fifth, it's an odd power, it's going to actually cross the axis. So instead of just turning around, it's going to go through the axis. So if you're looking at it, you've got that it could either go straight through, and that usually happens if it's to the first power, so x minus r to the first. And your other option is that it could kind of make a curve when it goes through, kind of flattens out. And that's usually what happens if it's higher degrees. So like the third, fifth, seventh, something like that. And the higher the degree, the flatter it kind of gets at that point. So we've got two other things here. It says if f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. Turning points is another way of saying mins or maxes. So if we had something that was a degree of, let's say, 8, then that would mean that we had at most 7 turning points. You have n minus 1. So if it's degree n, degree 8, you would have 7, 8 minus 1, 7 turning points. And so your polynomial can make any kind of curved shape, and your turning points are your mins or your maxes. It's where it turns from increasing to decreasing. That's why we call it a turning point. It's where it kind of turns around. It turns from going up to going down. And the next one goes the other way around. If a graph has a n minus 1 turning points, if it has a certain number of turning points, then you can add 1 to figure out what the degree is. So let's say that we have, I'm just making up numbers here, 12 turning points. Then I can add 1 to get 13 as the degree. So if you know the degree, you know at the turning points. If you know the turning points, then you can know the degree. But do keep in mind that it's saying at most here, and it's saying at least here. So it's not always one away, but most of the time it is. And then the other thing about polynomials is that based off of the total degree of the polynomial, you can kind of figure out what the end behavior is going to look like. And that's kind of what this table is right here. So this right here is talking about the total, that total degree. And when I'm talking about positive and negative up here, this is talking about the leading coefficient. So if you have an even polynomial, so that means that when you multiplied it all out and it looks kind of like this one did up here, where it's all multiplied out, you're talking about like this part right here. So you're looking at the leading term. And so the degree, the total degree would be that cubed, and then the leading coefficient would be 1 because there's not a number in front of the x cubed. So if it's even and it has a positive leading coefficient, then you're going to start in the top and end in the top. You can do whatever it wants to in between, but you're going to start and end in the top. If it's even and negative, you're going to start and end in the bottom. Same thing, it can do whatever it wants to in the middle, but you're going to have a starting point in the bottom and ending in the bottom. If it's odd and positive, you're going to start in the bottom but end in the top. So you can have whatever is going on in the middle, but it starts and ends in those spots. And odd and negative does the opposite. You guessed it. Starts in the top and ends in the bottom. So kind of knowing all of these characteristics, let's see if just by looking at this equation, we could figure out what the graph could be for this polynomial. So if you look, we don't even know what all of the coefficients are. We've got an A right here, and we've got a B right here. We don't know what they are. We just know that they're positive, and it says which of the graphs could be this graph. So what really matters is that we know the leading term, which is that x to the fourth. Remember, the leading term is the one that has the highest degree. And if you look, that highest degree is 4, which means that we're looking at an even function. So you can see all of them start and end in the same place, just like our even functions do. And our leading coefficient is 1, which is positive, which means we're looking at this part of our table. If it's even and positive, it's going to start and end in the top, which means we can go ahead and get rid of that one. The other thing that we also know is that since the degree is 4, we should have at most 3 turning points. So I can look here, I've got 1, 2, 3, 1, 2, 3, but this one has 1, 2, 3, 4, 5, so we can get rid of this one. That one has too many turning points. So we've narrowed it down to the first 2. Then the last thing that's going to help us is that even though we don't know what A and B are, we can find our y-intercept by just plugging 0 in for x. And remember, when we plug 0 in for x, that's going to get us 0 to the fourth plus a times 0 cubed plus b times 0 squared minus 5 times 0 minus 6. So all of those terms that have coefficients just end up disappearing because they've all got 0. So 0, 0, 0, 0. So it doesn't matter what a and b are because all we're left with is -6. So my y-intercept should just be 0, -6, which if you look, this one has a positive y-intercept and this one has a negative y-intercept. So we can get rid of a and it's got to be b. So you can figure out what the intercepts are, and that can kind of help you a little bit. So like I said, up here, it's helpful to know what your y-intercept is and how to figure that out, even though maybe it doesn't help you with what you're finding in other parts of the problem. Okay, now we're going to go the other way around. We're given a graph, and now we need to write the polynomial that goes with it. And if I'm looking, that's kind of what we had up here with example 2. We're going to match our x-intercepts with some factors and see if we can get an equation. So I've got -2, 0. So that means x equals -2. I've got 0, 0. So x equals 0. And I've got 2, 0. So x equals 2. The other thing we have to pay attention to, though, is how they touch or how they cross the axis, because that is going to change a little bit what we write. So if I have x minus 2, I can go ahead and say that that is x, or sorry, x equals -2. I can go ahead and say that's x plus 2 when I put it in my parentheses. If I have x equals 0, that one is just x. I could put x plus 0, but that plus 0 isn't really going to help me at any point, and it's just going to make it a little more complicated when I go through and try and solve and simplify my equation. And right here, if I have x equals 2, that one's going to be x minus 2. If you look, this one bounces, which means it's got to have an even degree. From our table that we have up here, if it bounces, it's got to have an even degree, which means it's got to at least have a squared with it. And our directions do say to write it and use the smallest degree possible, so we are going to use the squared. If we're looking at our 0, 0, that one does just go straight through. So that one can have the first power. And our 2, 0 goes straight through, so that one can also have a first power. So I'm going to come up here, and I'm going to have y equals, and I can put all these together. I'm going to put the x first, then I'm going to put the x plus 2 squared, and then the x minus 2. If they have exponents of 1, you don't necessarily have to put those exponents there. It's an understood 1. Then the only thing that's missing here is that there might possibly be some number that we're multiplying by in front. So if you remember when we had our quadratics, we would always have like an ax squared value, and we would have to kind of figure out what that was. And if you remember, we would use some point in our vertex when we were doing our vertex form to kind of figure out what that a value was and then plug it back into our equation. And so if you look, we do have another point, -1, 6. So we're going to plug that in to see if we can figure out what a is. So I'm going to plug that in for x and plug that in for y. So I'm going to have 6 is equal to a times -1 times -1 plus 2 squared times -1 minus 2. And I'm going to solve for a. So 6 equals a times -1. -1 plus 2 is 1 squared, and -1 minus 2 is -3. 1 squared is just 1, so 6 is equal to a times -1 times 1 times -3. -1 times 1 times -3 is a positive 3. And then I can divide both sides by 3 to get that a is 2. So when I write my final equation, I'm going to plug that 2 in for my a. So y is equal to 2x times x plus 2 squared times x minus 2. The order of these parentheses doesn't really matter, but if you have an x that's outside of the parentheses, you do want to put that in the front with whatever your a value is. And then we've got just a couple more here. It says, analyze the factored form of the polynomial function. What is the degree? How many turning points does it have? What is the y-intercept? And what is the x-intercept? Or what are the x-intercepts? So if we're looking at ones that look like this, I don't know about you, but I don't want to have to multiply it all out to figure out like what the degree is and get that leading term to get the leading coefficient and all that information. So there is an easier way to find the degree. If I want to find the degree, I'm just going to take the degree of each of these parentheses on their own and add them up. So remember, if one's not written, it's an understood 1. So I would just do 1 plus 1 plus 2, and I would get that the degree is 4. So if we have a degree of 4, that means that our turning points would be at most 3. Okay, we've kind of already talked about it, but to find our y-intercept, we're going to plug 0 in for y, or sorry, for x, to find the y-intercept. So that means I'm going to have 2 times 0 minus 1, 2 times 0 plus 1, and 0 plus 3 squared. So 0 minus 1, 0 plus 1, and 3 squared. So -1 times 1 times 9, so -9. My y-intercept would be 0, -9. And then remember, our x-intercepts is just each of the parentheses set equal to 0. So 2x minus 1 equals 0, 2x plus 1 equals 0, and x plus 3 equals 0. Over here, I can add 1 to get 2x equals 1, and divide by 2 to get x equals 1/2. Subtract 1 to get 2x equals -1, and divide by 2 to get x equals -1/2, and subtract 3 to get x equals -3. So when I write them all as points, it's going to be 1/2, 0, -1/2, 0, and -3, 0. And then for the last two, we're going to kind of go the other way. It's going to tell us the information, and we're going to have to write the equation. So it says form a polynomial whose zeros are -3, 5, and 8, and whose degree is 3. So remember, if we have that it's -3, that means x equals -3. If we have 5, that means x equals 5. And if we have 8, that means x equals 8. So my parentheses here would be x plus 3, because I would add 3 to the other side. Here I would have x minus 5, and here I would have x minus 8. Which, if it's telling us that the degree is 3, that would make sense because we've got 1, 2, 3 parentheses that all have a degree of 1. So if we follow the same rule that we did on example 6 and just add them together, that would give us the degree of 3. But to form that polynomial, we do have to multiply all this out and get down to our y equals and x to some power plus or minus x to some power and get all of our terms. So I'm going to start by foiling. Let's do these two first. Honestly, it doesn't matter which two you pick to do first. You just got to pick two of them to do. So we're going to start with the blue and the purple. So I'm still going to have my x plus 3 over here. And then over here, I'm going to have x squared minus 8x minus 5x, and then plus 40. So that's going to give me x squared minus, I have 8 and 5, that's going to be 13x plus 40. And then we've got to distribute out that x plus 3. So we've got x cubed minus 13x squared plus 40x, and we'll do blue, plus 3x squared. If I have 3 times negative 13, that would give me negative 39. And 3 times 40 gives me a 120. Yep. So from here, we just got to combine our like terms. So I've got a x cubed. Then I've got a negative 13x squared and a 3x squared. So that's going to be negative 10x squared. I've got 40x and negative 39x. So 40x minus 39x is just x. And then plus 120. So when we write our final equation, we're just going to put y equals in front of that, and we've got our answer. Now, where you do have to be a little careful is sometimes when the degrees are different. So this one just said whose degree is 3, so it was pretty easy. We had 3 zeros, and so each of them would just have that 1 for their degree for each parentheses. Example 8, it says form a polynomial whose zeros and degree are given below, but notice it's talking about multiplicity. So that's specifically telling you that this 0 has this multiplicity, and multiplicity is just telling you what degree goes with that parentheses. So if it says negative 3 with a multiplicity of 1, when I have x equals negative 3, and I get my parentheses of x plus 3, that multiplicity of 1 just means that I would have an exponent of 1. Here it says 3 has a multiplicity of 2, so if x equals 3, my parentheses would be x minus 3, but the multiplicity of 2 would mean that it needs to be squared. And then 5 with the multiplicity of 1, that means x equals 5. My parentheses would be x minus 5, and the multiplicity of 1 would just be a 1. So if we're looking for that degree of 4, I would have 1 plus 2 plus 1, which would get me to that 4. So whenever it says multiplicity, they're just telling you what the degree is for that specific parentheses. But notice when we've got to multiply it out now, we're still going to have the x plus 3, but since this x minus 3 was squared, we've got x minus 3 times x minus 3. We've got it twice, and then the x minus 5. So I'm going to FOIL out those two together and those two together. And then when I get that, I got to FOIL out all of those answers together. So with the green, I get x squared minus 3x plus 3x minus 9. So that's going to give me x squared minus 9. That's kind of nice. The insides cancel. With the orange, I get x squared minus 5x minus 3x plus 15. So I get x squared minus 8x plus 15. And let's do our last step in purple. So I'm going to distribute my x squared. So x to the 4th minus 8x cubed plus 15x squared. And we'll do the negative 9 in pink. So minus 9x squared. Negative 9 times negative 8x would be plus 72x. And negative 9 times 15 would be minus 135. So now when I combine all my like terms, I just have the 1x to the fourth term. I also just have 1x cubed, so minus 8x cubed. I do have these x squared terms I can combine. So 15x squared minus 9x squared is going to give me plus 6x squared. And then I just have a 72x and the negative 35, so there's really actually not a whole lot you can combine here. So plus 72x minus 135, put your y equals in front of it, and you're done. There we go. So the nice thing about these is you don't have to worry about like an a value because it's not giving you a graph like this one up here did where you've got that extra point. So that's it for our first day of polynomials. We're taking things that we've been working on throughout this year. So like talking about how to find your zeros, talking about when it's above and below the axis, so greater than 0, less than 0, and then talking about how to like get equations from graphs and all that kind of stuff. We're just kind of stepping it up a little bit with our polynomials. So make sure that you get started on your assignment, and please make sure to ask me questions if you have them. I know this is kind of a lot in this one day. So please, please, please ask me questions. We've got plenty of time in class that you can ask me, and we've got tutoring times that you can come and ask me. So get started on your assignment, ask me questions if you have them, and I hope you guys have a good day.